So let me start by that to begin with. And this is you can see we are the Earth, at the Earth looking at a distant star and the light bending by the sun. This was the prediction of Einstein's theory, which was convincingly demonstrated and made Einstein's general relativity something people began to take seriously at this point. The thing I want to talk about particularly is the effect on the background sky. And here you see the bending of the light means that you see here we have maybe a circular pattern. Imagine you had a circular pattern of stars, and that if the sun was not there, they would look circular. But as the displacement outwards gets less and less, the further away you get from the sun, it means that the bending of the light means it looks further out than the image does, but it's less further out at the far point than in the near point, and so it becomes elliptical. So the shapes become distorted, circles become elliptical. And this is a feature of the Weyl curvature of space-time. So this is the particular feature which I want to discuss. The curvature of space-time naturally splits into two. I should say that I became interested in general relativity partly because of my relationship with Dennis Sharma that was mentioned already. And he got me interested in physics when I was doing pure mathematics, really, algebraic geometry. But I loved the physics, and particularly Einstein's general theory of relativity. But I remember I had ways of looking at tensors using drawing little diagrams and things like that. But I learned about two-component spinors, and I thought, how on earth does that make any sense? And I puzzled about it for a long time until I went to a course of lectures by Dirac in quantum mechanics, where he deviated from the normal series of lectures and talked about two-component spinors and made it absolutely clear to me. Then I went and started to translate the tensor formalism of general relativity into two spinors, and it became very clear that you have these two kinds of curvature. The curvature, which is the Ricci curvature, is, according to Einstein's theory, directly determined by the matter distribution, whereas what's left is the Weyl curvature. That's the distortion part, which we would have seen in the previous picture here, the fact that you have circular shapes become elliptical, so it's a distortion. And this distortion is the Weyl curvature. It's the conformal curvature, and that's going to play an important role in what I want to say later. But the Weyl curvature describes the free gravitational field. It's a bit like Maxwell's equations, where you have the source and you have the field itself. The charge current vector is the source, and the field is the electromagnetic field tensor. But there are different orders of derivative, whereas in general relativity, the source and the field are at the same order of derivative. So you see the source playing one form of curvature and the free gravitational field forming the other. And the Weyl curvature is really the free gravitational field. So that point of view was something I really picked up thinking about gravitational lensing. And let me move on. I'm just going to talk mainly about four-dimensional geometry. So you have to get used to that. And therefore, I'm seeing three spatial axes and one time axis. But the more important thing are the light rays. So I have to use this. If you're using, say, seconds for your time, then it's a good thing to use something like light seconds. In other words, whatever it is, 380,000. No, I get my figures wrong. Anyway, a long distance for your light second. And that's convenient because then your light rays, you can draw nice pictures. That's the basic point. And I like to draw nice pictures. That's the important feature. Okay, the light cone, that's the most important feature of the geometry. We'll come back to that later, but I want to say particularly you imagine your space-time to have these cones. Of course, because your space is four-dimensional, you always have to imagine there's an extra dimension, so drawing them as cones like this is not quite honest because you're only looking at two spatial dimensions where you really have to have three. So you've got to bear that in mind all the time. And you bear in mind also that light rays follow the history of a photon will be along the light rays, tangent to the cone all the time, whereas material particles, finite mass particles, will be within the cone, and so you'll have curves representing GD6, not necessarily GD6, could be curves, time-like curves within the cones. And this gives you the causal structures to space-time, which is given by the light cones. Now, one feature I want to mention particularly, if you have well, I should call these really null cones. The null cones are at each point that's in the tangent space. The light cone, in a sense, is really the locus of the null GD6 through a point. And the point I want to make is that they can do funny things. At the back, you notice a crossing region and cuspidal region like this. So the natural feature, when you have a lot of curvature, conformal curvature, you will get unpleasant looking features like this. So, and there you have another picture where they start to cross over. The trick is not to worry about that too much. When they start crossing over, you forget about what happens on the inside. This next picture is a picture of a Oppenheimer-Snyder gravitational collapse, which was mentioned earlier. This was in just before the war, 1939, when they studied a dust cloud collapsing and spherically symmetrical. And so the fact that all the matter you see at the bottom, I should explain, my pictures are normally with time going up the picture so that we have a collapsing material, which in Oppenheimer-Snyder picture was a dust cloud. Since it had no pressure and everything was focused towards the central point, it's not at all surprising that you get infinity for the density, because where does it go? I mean, it's falling inwards, nothing to stop it. And since all the matter is focused into this one central point, the density is bound to become infinite. Now, this may be an artifact, and I think a lot of people did think it was an artifact. And I remember becoming interested in it, particularly when I started a fellowship at Cambridge, St. John's College, Cambridge, and I attended a lecture given by David Finkelstein that Dennis Sharma had told me about, and he was describing mainly what I'm using in this picture here, the upper part of the picture. You see this cylindrical thing which represents the history of the event horizon, which is really where the cones become tangent to this. Well, you might, the time vector field is pointing upwards, and so it becomes, it's time-like out here, but when you get inside, it becomes space-like, and it's null just on the horizon. And the main point is the cones have become tangent there, so once you've fallen through, you can't get out again because the world lines are all pointing through into the center. Now, of course, the question was, and certainly as was mentioned in the introduction, you have this in the early 1960s, people started to see these curious phenomena, which seemed to be the quasars, which we now call them quasars, quasi-stellar objects, which had intensities of more than an entire galaxy, and yet they seem to be pretty small, concentrated in a region. From the variations in brightness, you could see they couldn't be that big. They had to be smaller than the solar system, something like that. And so people were beginning to talk, particularly Hoyle and Fowler, I remember, speculating on whether these might be collapsed features, but where it's complicated and not symmetrical, and you might get radiation coming out from situations like that. But the question arose, was this symmetrical collapse generic or not? And do the presence of features like this cause problems? And I began to think about it, and this is the picture taken from the paper that was referred to in the introduction, which seems to have won me a Nobel Prize, which was well, I did the work in 1964, and I gave a talk at King's College. I remember the great geometrical relativist John L. Singh happened to be there, and I was very flattered that he was attending my talk. Despite what the movie says, Stephen Hawking was not present, but I did give this talk, and Dennis Sharma heard about it, and he suggested I give a repeat in Cambridge. The feature I want to illustrate here is, first of all, we have an initial surface, which is a space-like surface, which you imagine is non-compact. It could go out to infinity like this. You're only looking at a local region within this initial surface. the matter collapses inwards, and at a certain point, illustrated by this ring in the middle, this is what I call the trapped surface, and you can see that the local future of that ring is bounded. This shaded region would be the future of that ring, where you can get to from time-like curves, and I would look at the boundary of that region. And the trapped surface meant that the rays start to converge inwards at that point. This, more specifically, you see the surface, not just, you see it looks like a ring, but of course that's because I've not drawn enough dimensions. But you have to imagine there's an extra dimension, it's really a surface. And if you have a surface, it might be concave on one side, and then a flash of light over that surface, you would expect it to converge, but on the other side, you would expect it to diverge. What's particular about a trapped surface is that it converges on both sides. There's nothing actually strange about that. It may seem strange at first, nothing really strange, because if you have, say, 2 points in space-time and look at their past light cones, their intersection will locally be trapped, because the light rays which come out from a flash of light on that surface would be focused either to P or Q, and therefore converging on both sides. What's peculiar about a trapped surface is not that the light rays are focusing on both sides, but that it's that and compact at the same time. So here you have a surface which is not compact, so it's not surprising. But if it closes up, then you're in trouble. And that was what I was able to use that feature and derive a fact that you have to have a compact region here. And I won't go into the details of that. But it did depend upon the fact that when you have rays that start by converging inwards, and if they're hypersurface orthogonal, that really means they're in boundary locally to a 4 volume. As they focus inwards, they continue inwards, unless the energy density becomes negative. So you assume the energy density is never negative, or at least the flux across the light rays is never negative. And then it's really this effect due to Rashiduri. So we go back to India again. This is the null version of this effect. And you can show that the light rays then must eventually converge. And using topological ideas, you can show that there's a contradiction. People often used to worry whether you would get a trapped surface. Maybe things go wrong before that. But it seemed pretty clear, certainly after many discussions with Charlie Misner, I remember, who was an important figure in this discussion, because he persuaded me that it can't be a real problem. People used to talk about stars mainly, and this is where, of course, Chandrasekhar's work with the white dwarfs, and if they got too massive, then you would have a problem making them stable. But it was a feature which would apply not just to stars, but you have whole collections of stars. You might imagine many, many stars. And if they get reasonably close together, you don't need to have all that many stars, all that close together. They don't have to intersect or anything like that. And you can see, not necessarily a trapped surface. It's easier to think of the focusing point. You think of point in space-time, and as the future light cone of that point, I don't know if my cursor is being seen here. I'm having trouble seeing it myself. Here we go. The future light cone of that point, the point has got off the picture somehow. And the light rays, as they cross the stars, become, and if you have enough stars, they'll begin to refocus. And then yes, here we have a point there, and the light rays from that point begin to refocus because of the number of stars they encounter. And the density doesn't have to be large or anything at all, and you will get this reconverging light cone. That's just as good as a trapped surface. In that condition, the theorem just works just as well. Okay, well, Stephen Hawking got involved with this. Let me just backtrack a little bit from my picture here. Stephen Hawking heard about my talk from Dennis Sharma, and he then started to develop my techniques and using the arguments to apply to the Big Bang, as well as to a local collapse. He picked up them very quickly, and he used the same theorem as mine in a reverse direction of time to show that in certain circumstances you would generically get for a collapsing universe, if you like, if you imagine it could perhaps bounce somehow and come out again without being singular, this won't work under very general circumstances. And after he generalized these techniques and applied them to general relativity, to cosmology, and And then we got together and produced a theorem which encompassed pretty well all the things we had before. So it's a very general result. Now, I want to talk about quantum mechanics and general relativity because people used to think, well, you've got these singularities. In fact, that was really what I proved, not the fact that, although the Nobel Prize was for black holes, it's another condition that you have to, the mere fact that you get a singularity doesn't mean you have a black hole, because you had to show something which is still unproved as far as I'm aware, this thing called cosmic censorship. That can you get naked singularities? I used to puzzle, it didn't seem to me completely obvious that you wouldn't get naked singularities under general circumstances. I got gradually convinced that they weren't the case and that cosmic censorship in some form was probably true, but it's not a rigorous theorem at the moment as far as I'm aware. So we still don't know that naked singularities don't occur. I think it's most unlikely that they do, and you can produce many sort of hand-waving arguments to show that it's unlikely. Anyway, let me continue with this. What do you do with the singularities? Well, the normal thing people would say, well, you have to bring quantum mechanics into it, because classical general relativity says you get singular, the densities become infinite, therefore the curvatures become infinite. Well, when you get radii of curvature, which are something like the Planck distance, so the radius of curvature becomes 10 to the minus 33 centimeters, that's ridiculously tiny, then you've really got to worry about quantum mechanics. So perhaps you don't really have singularities, but some quantum gravity effect. So is it to do with quantum gravity? And this is the point I want to raise. So we're trying to bring quantum mechanics and gravity together and produce a theory which explains away the singularities in some, and this would apply, so the argument goes, not just the singularities in black holes, which we can't really get at because they're in the black holes. Maybe when Hawking evaporation takes over, you might have some effect that you could see ultimately. But the real argument would perhaps be to the Big Bang. And this certainly was what Dennis Sharma began to persuade people about. And so you need a theory which combines general relativity with quantum mechanics. Well, we don't have a good theory. There are all sorts of ideas, string theory, loops, foams, things like this. Whatever one might think of any of these particular theories, they're certainly very far from any observational consequences. But so I'm not going to talk about that. I'm going to talk about something else. The main reason I'm not going to talk about that is that I don't think that it solves the problem. And the main reason I don't think it solves the problem, well, what is the problem? The problem has to be how we deal with the Big Bang, because, okay, we may deal with the singularities in some way, but the more immediate problem is how do we deal with the Big Bang? And the trouble I have always had, well, always, certainly for a long time, is that the Weyl curvature, and this is the gravitational degrees of freedom, seem to go to zero at the Big Bang, or close to zero. They seem to be strongly, I'll say a lot more about that in a minute. Whereas in the singularities in black holes, the expectation is that the Weyl curvature violently goes to infinity. So what kind of a quantum gravity theory is it that produces those so completely different answers in these two different situations? And this was a very crucial feature for me to worry about. Sorry, I keep moving it the wrong way. Here I have, looking at it from a rather different perspective. The point of view I'm thinking about is not really so much what this theory in the middle is, that is to say, what is the mysterious quantum gravity which relates these two theories, but what are the problems of the two subjects? All right, we see this problem in general relativity is singularities, but there's a problem in quantum mechanics. And this problem, in my view, the main problem in quantum mechanics, I mean, you get divergences, all sorts of things like that, but the main problem with quantum mechanics is the measurement problem. And so I have at the top a cartoon of a cat which is dead and alive at the same time. It's not the usual way one thinks about it, but you see the cat is on one side dead and on the other side alive. And this is the measurement problem in quantum mechanics. I will come back to this briefly at the end of the talk. This is not my talk today. There's a lot can be said about this. And I think that general relativity really is the thing which answers the question of the measurement issue in quantum mechanics, but that's not what I want to talk about here, although as I say, we'll come back to it. But the main thing I will talk about is the issue of the singularities in general relativity. And okay, I said the singularities in general relativity. What about the Big Bang then? Well, this is a cartoon of our current view of the universe. Well, I'll come back to what happens right in the Big Bang shortly, but the main thing is that we see this expansion. According to Einstein's general relativity, gradually slows down and then starts to accelerate from the observations at the turn of the century that of the distant supernovae stars with these two groups. Notice that they seem to indicate there's an accelerated expansion, which to me is simply an evidence that there is a cosmological constant in Einstein's equations. I remember I always got very puzzled by people saying there's this mysterious dark energy going around, who knows what it is. When I used to go to conferences and people would say at the end of the conference, well, we don't yet know whether there is a cosmological constant in Einstein's equations or not. Perhaps by the next conference we will know. And when people found this evidence, they stopped talking so much about the cosmological constant and thinking about it might be something else. Of course, it might be something else. But to me, it was a great revelation because I had wrong reasons for believing it should be zero. And I think it was Jerry Oestreicher who persuaded me that it was not just a supernovae. It seemed to indicate that there was this accelerating expansion, that when you introduce this term, it really did make a lot of things work so much better. And I became convinced, okay, let's shift my point of view and take the cosmological constant seriously. But I do want to talk just initially about what most cosmologists seem to think about the Big Bang, a little bit more about this picture. Namely, you should have a good look at the Big Bang a lot more closely, and what you would see would be this inflationary phase. So current theory takes inflation seriously. I could never take it seriously because it really, well, I'll mention a problem I have about it in a moment, but there were some various reasons, some which are more convincing than others. I think that getting rid of the monopoles I never found very persuasive because you had a theory which had the monopoles in the first place. The other argument that people often, well, the main argument is the scale invariance of the microwave background, which I'll mention if I have time at the end. If you don't have inflation, you've got a problem about why are these temperature variations in the microwave background have this very curious scale invariance, which seems to indicate some kind of exponential expansion as an origin for it. But one of the other arguments that people use is, okay, the Big Bang could have been very complicated and maybe all sorts of wild Weyl curvature, whatever you like, but then the inflationary phase would have smoothed it all out as smooth as nice, and then we have this very smooth looking Big Bang that we seem to experience. I never believed that argument for the following reason. Okay, let's turn the universe upside down. All these equations, including the inflaton field and everything, are symmetrics in time. So if you have an expanding universe as a solution, then you have a collapsing one. But you would expect to have irregularities. And in a collapsing situation, these irregularities would build up. You expect things to form. Certainly, as the universe gets very, very concentrated, you get black holes formed. These black holes will collide with each other. A great mess of complicated singularities will congeal together, and it won't look anything like that. Sorry, I keep pressing the wrong button. It'll look much more like that. You get these black hole singularities congealing with each other, violently diverging Weyl curvature, completely unlike what we saw in the Big Bang. And because of the time symmetry of the equations involved, why was not this the case in the beginning? In fact, you can work out how unlikely the situation that we seem to see, namely that, as opposed to this. I remember Don Page doing a calculation for me. See, how many black holes do we see? I mean, how many black holes do we expect to see in our universe, judging from the galaxies we see within our particle horizon and so on. And Don Page came up with a figure of an entropy of something like 10 to the power 123. I think with the dark matter, it's something like 10 to the power 124. So since the entropy is a logarithm of a probability, the probability of finding something nice and smooth like this, as opposed to what the more likely situation would be this, is something like 1 part in 10 to the power 124. So various religious people said, well, look, I proved religion because this tells you that there must be a God who, that was not my view. I think there must be some other explanation. I toyed a long time with the idea that there must be some very, very curious kind of quantum gravity, which is very asymmetrical in time. And then I sort of gave up on that and said, well, maybe you just postulate for some reason unknown that the singularities in the future are allowed to have wildly diverging Weyl curvature is the generic case, whereas for some reason unknown, the Big Bang has to have a vanishing Weyl curvature, which was my Weyl curvature hypothesis, simply a hypothesis with no, well, let me talk a little bit more about that. You see, it's very remarkable, not just for the reason I mentioned, but also for the following. Think about the top 3 boxes here. Imagine a gas in a box, and you go from left to right, unlike my other pictures where time goes up, here time is going from left to right. Imagine in this box, we have a smaller box where you have all the gas which is collected. Then you open the box up and the gas spreads out through the box. This represents time increasing from left to right, entropy increasing from left to right. Okay, let's imagine now a different situation, a galactic scale box full of stars, and these stars are now gravitating. They will tend to clump because of the universally attractive feature of gravitation. They will start to clump and they will produce black holes. So the entropy is still going up and up, time going from left to right, but the picture looks completely different. What we see is a combination of bottom left and top right. It's not just that the entropy was low in the early universe, it's low just in gravity. Very, very odd. Why is it that's so curiously imbalanced with regard to gravity? It's even more striking because when we think of, well, we go back to whatever it is, 380,000 years after the Big Bang, just when the time for the radiation can escape out. And this is I think the original, was it the Kobe satellite? I think when it looked at the microwave background, and you see this is the intensity for different frequencies, frequency going up here horizontally, and you see this wonderful Planck curve. These are error bars, and we notice that the error bars are exaggerated by a factor of 500, so they hug the incline even right at the end. It still hugs the incline right through the center of the incline. It's an amazingly accurate Planck curve. Why is it such an accurate Planck curve? Well, it's because, so we see that what you have is thermal equilibrium. So it's not just that when you go back and back and back in time, where the entropy seems to come down and down and down and down and down until you get a maximum. It seems to be most peculiar like that. It's a very strange argument. People might say, well, if the universe was much smaller in those days, maybe, no, that doesn't work. That's not the explanation. It's just very peculiar that the radiation, as in the picture I just had previously, where we see the, not just a gas in a box, but if you have oh yeah, I'm going the wrong way. I never get the hang of these pictures. Not just the gas in the box, but when you think of radiation and the gas, the box, it's still maximum entropy. It's just gravity, which is not. Somehow gravity is singled out as being very peculiar. Okay. Now I want to take a different perspective on the whole subject. The perspective is the conformal perspective. So I want to say it's important to look at space-time with regard to the conformal structure. This picture is a nice, wonderful picture due to M.C. Escher. It's the first of his circle limits. I think he thought that this was rather primitive, this one, because it's his later ones were much more ingenious in many ways. But this illustrates the geometry very nicely. This is a geometry of the hyperbolic plane, and it's the Well, the the Beltrami Poincaré, Beltrami was first, if you like. People usually call it the Poincaré disk. And you see the hyperbolic geometry squashed up conformally into this nice disk. And these fish creatures have circular eyes to illustrate the fact that it's conformal. The conformal squashing of the eyes, they remain circles right as close to, I've actually seen the original of this picture, and extraordinarily well done, how precisely it's right up to the edge. You can't see it so well in this reproduction here, but it is extremely accurately done. And the conformal picture tells you that you could talk about infinity. And I was really very fond of that idea and could make use of it in all sorts of ways in relativity theory, usually to do with radiation theory. But let me just go back to the light cone and say, how do you represent the geometry of space-time? Well, it's not just the light cones, but you have to have these surfaces here, which are the surfaces of equal time from the origin. So you have the cone represents 9 out of the 10 components. It's actually the 9 ratios, the 9 independent ratios of the 10 components of the metric. The 10th component is the crowding of these surfaces. What are the surfaces? Where they represent, if you have, hello? Sorry, is that all right? We have 2 particles going through this origin point at different speeds, if you like, great relative speed, near the speed of light, but not quite the speed of light. And as these surfaces intersect, as these 2 particles intersect these surfaces, let's suppose they're identical particles, then these surfaces represent the ticks of the clocks. And the ticks of the clocks, well, I'm just using Einstein's, the 2 most famous formulae of 20th century physics, E equals mc squared, of course, E equals h nu, Max Planck's formula. Put the 2 together. The first, Einstein tells you energy and mass are equivalent. Planck tells you energy and frequency are equivalent, therefore mass and frequency are equivalent. So these surfaces are telling you that particles are wonderful clocks. They're very, very precise clocks. And this gives you nuclear and atomic clocks, scaling the things down adequately so you can actually see them properly. But it's the scaling that you get from the mass of particles. But if you don't have mass, then you don't need the surfaces. So if you're talking about photons, and even if you're talking about Maxwell's equations, you see Maxwell's equations, that's, if you like, the photons, if you think of them as classical particles, they just zip along with the speed of light. But if you think of them as quantum particles, they are really solutions of Maxwell's equations. And Maxwell's equations are conformally invariant. So you see that it's just the light cones. The conformal structure is the light cones. That's the point I'm trying to make, is that in general relativity, conformal geometry is more primitive than the metric geometry. It just means you have the geometry of massless things, of photons, if you like, or any mass, even gravitational radiation, basically follows the light rays and is, in a certain sense, conformally invariant. I won't go into the details of that. So it's the light cones. Now, what I'm going to do here is that trick, the Escher trick, if you like, as applied to infinity. When you have a cosmological constant, this is an important factor here, and it was important for me to realize and take seriously the cosmological constant, because that means that the future infinity is not null anymore, it's space-like. And when it's space-like, it's like a time. It's time infinity, but it's like a time. And the photons, if you like, go and they meet that time. And you might wonder what happens to them as they go beyond. I did wonder about that. That was a question. But this is the picture of the universe. And there's a wonderful theorem by Helmut Friedrich, which tells you in very, very general circumstances, as long as you have massless sources and you don't have things like black holes, if you've got rid of them somehow, then you will have a nice space-like boundary in the future. Now, what about the Big Bang? Now, this was Paul Todd, my graduate student at the time, had a better way of looking at it than saying the Weyl curvature hypothesis. He said, why don't you just say that the Big Bang stretched out is a nice smooth surface? And that seemed to be a much nicer way of doing it. And I agree with that. So let's do it that way. You can stretch out the Big Bang, you can squash down infinity. But it's also that you see you can continue the infinity. The usual picture is that you don't imagine there's anything beyond it, but you could in principle continue. And it's very useful to do your equations. You can just imagine this is part of a surface which keeps on going. In the same way you can imagine the past, you could imagine it keeps on going. And it's a nice way to talk about your equations. That's all it is. It's a trick. But then I remember worrying about this one point. Is it just a trick? Or could it be more than a trick? You see, when you stretch out in the Big Bang is very, very hot and very dense. The conjugate variables to the space and time are the momentum and the energy, and they go the other way around. So when you stretch out space and time, you squash down energy and momentum. So your temperature, which is enormously high, when you stretch it out, it becomes colder. The opposite thing at the remote future is that when you squash infinity down, the density becomes much bigger and the temperature becomes much bigger. So they actually begin to look very much like each other. So I thought they did look very much like each other. Maybe in some sense they are like each other. I don't want to join them out together. This gives you horrible problems with closed-like time-like curves. But if you imagine that our Big Bang was the continuation of the remote future or previous eon, I'm calling it, that would maybe make sense. It's a radical idea. And I spent a lot of time giving lectures on this and thinking, well, nobody will ever prove me wrong, so I can talk on indefinitely on this subject. But then I began worrying about, well, I should come back to the inflation point. You can't have inflation in this picture because it actually that spoils the join. But however, you do have an exponential expansion. You see, in the previous eon, you have this exponential expansion here, which sort of looks like an inflationary phase. So maybe you don't need inflation because the fact that you have the scale invariance as a motivation for inflation, you can do it a different way, that the scale invariance comes from the exponential expansion. Signals can get across as long as they're massless. So you can imagine photons getting across, provided the frequency is sufficiently low, maybe magnetic fields and things like that could get across. Otherwise, they have trouble on the other side. They scatter and don't get very far. Gravitational signals might get across. So this is an important factor. What about gravitational signals? Well, I began to think about it. What about collisions between supermassive black holes? Here I'm having the crossover from one eon to the next is this surface in the middle. And I'm imagining this is us at the top looking back, and this is a stretched out Big Bang. And do we see possibly signals from gravitational waves coming from the collisions between supermassive black holes? Now, you have to wait a long time for this to happen, but in a single cluster of galaxies, the clusters you have this exponential expansion, so the superclusters will disperse, but the clusters remain more or less bound. And so that there will be several collisions between supermassive black holes in a single cluster. So you might see several of these. They would look at the bottom picture I've drawn rather deliberately, rather faintly, the sort of thing you see. You see these rings, which would be the evidence of these gravitational wave signals, according to the theory. And if you see several of these collisions, you might see concentric rings. So that was the test. And various people started to look at these things, but didn't see anything until my colleague, Armenian colleague Vahe Gurzajan, had a look. I wanted to show you this picture. This was from the, I think the WMAP data, and the equatorial region is removed. That's the galactic plane, and so in order to get rid of the galaxy, that's removed from the picture. But you see these regions of these rings. And I forget, you probably see the numbers there. I can't see them myself, but the test that I had here was that you consider that you twist the sky. You do the same test for more and more twists of the sky. The twist is with an axis, vertical axis in the picture, and the twist increases as you go from top to bottom. And so this means circles become elliptical shapes. So you twist the sky, do the same twist on the twisted sky, and see the more and more you twist, the number of the signals drops dramatically. So with a substantial trick, you see hardly any of them. And they drop by a factor of 3, even with a tiny, tiny little twist. So this seemed to me a certain amount of evidence that these signals were right. A Polish group did a different analysis. I won't talk about that for the moment, but I will talk about this, which is the centers. This is now the Planck data. The previous one was the WMAP data. This is the Planck data. And I wanted to point out that these rings were singled out because of the variance being low, not because they were warmer or cooler, but the temperature variation around the ring was less than usual. And this would be an expectation from the theory. Now, the reason I'm saying that is that you see a clumping in the sky, which is very, very strange. If the whole sky was that uniform, whatever the reason, why do you get this clumping? Now, the picture is, in my scheme, is that the clumping is because there really are some very big super duper cluster regions where, let's look at the top plot. These are blue in color. It's always backwards, you see, because blue means cooler in the color coding and red means warmer, which of course is the wrong way around. Blue means red shifted and red means blue shifted. The blue ones are also the nearer ones. It's very confusing because, well, you see here, this is us up here looking back. This is the crossover surface. Here we have signals coming from a world line of a supermassive black hole, say. And if this is closer to us, then we're seeing the waves going away from us. So the more closer ones are the ones which will be red shifted. The further ones are the ones which will be blue shifted. So it's the wrong way around from what we expect. And so if it's doubly the wrong way around, so it's the right way around again. In other words, the red ones are the distant ones and the blue ones are the nearer ones. When I say nearer, I mean within our particle horizon. When I say more distant, they are outside our particle horizon. You can still see it because our light cone continues outwards and outwards to beyond the crossover to what we normally call our particle horizon. So you can actually see things outside the particle horizon. So that's one of the great powers of this. If it's right, then we can see things outside the particle horizon. But the point I want to mention here, which is remarkable, is that the clustering is in the color, and therefore, according to the theory, in the distance. So it really is a spatial clustering. This is also a spatial clustering. These are sort of intermediate greenish ones. If this is not the explanation, I need another explanation. But it is remarkable that it does seem to tie in if we allow for a certain amount of clustering, which is not part of normal theory. Okay, what about the other feature? This is the Hawking evaporation of a supermassive black hole. And this is, you might have to rate something like 10 to the 100 years, a googol years for some of the bigger ones. And here, according to Hawking evaporation, all the radiation goes out and goes out and it goes out and disappears with a pop or something like this. I should mention this one little point which people worry about, which is people worry about the Hawking evaporation and do you lose information? And I always thought this was I could never see how you could get around losing information because you just draw the conformal diagram. And if this black hole is big enough, you could fall into the black hole and play many, many games of cards and have all sorts of pieces of information in here. And that can't be repeated outside without violating the no cloning theory. So you've jolly well got to lose information. And I could never understand why people worried about trying to bring it back, particularly because, in my view, and this is the one point I wanted to make about the other side here, you see, you can lose information in ordinary quantum mechanics because whenever you make a measurement, you lose information. But people try to think, oh, well, nevertheless, it's somehow unitary. But with the gravitational being so important in black holes, the non-unitariness of the measurement process seems to be predominant feature. And so the fact that you lose information is quite consistent with what I would expect. I didn't want to stress that point particularly. The last thing I do want to say, however, is this question of the Hawking points. Do you see something about the Hawking evaporation? Now, in this is the picture from the paper written by Christoph Meissner, Pavel Nurowski, Daniel An, two Poles, and a South Korean who works in New York now. And this is the analysis, which is now published, I think, getting on for almost a year by now, in the monthly notices of the Royal Astronomical Society. This is the one picture we have in the article. Horizontal line at the bottom is the crossover surface. So this is the previous eon. This is our eon. This is the decoupling or last scattering. It doesn't make much difference. Surface here. Here is a Hawking. Here we have a galactic cluster, which has become a black hole, a supermassive black hole, sits around for, well, however long it is, 10 to the 103 years or something. And finally, it disappears. But you see all the radiation, it takes so long to evaporate away that all the radiation is concentrated in a tiny point. If you remember the Escher picture I showed you and how those fish get so quashed into the edge, all the radiation, because the light, the light cones are just squashed in there, they don't get very far. You may think of the radiation seeping way out to very, very long distances, the speed of light, but the speed of light is nothing, because the expansion is going so greatly that it's, when you squash it down, it's all squashed into a little point. So Hawking radiation or no Hawking radiation, all the energy would be squashed into that point. And so that you take and you can do integrals around it. You see, it's supposed to be smooth everywhere else. So the transition from one eon to the next is very smooth, and you get this smoothness everywhere except at the Hawking points. And these would be virtually singular points on the other side with the curvature. People would ask where the entropy goes. Where does the entropy in the universe go? It's in the black holes, it's in the black hole radiation. Where did it all go? It gets squashed into those points. When they come out on the other side, that is a less than a Planck scale, so it gets destroyed. So I'm certainly allowing the information to be destroyed there. However, the energy of that does not get destroyed, and you can see from the integrals it must not be. So you get this huge energetic point spread out, spread out, spread out to about, well, how big is that? That's about 4 degrees across the sky. At the top, we have a kind of contour of it. With it scatters and scatters and scatters. The photons don't escape because of all this wonderful work that my predecessor and Nobel Prize, Jim Peebles and his company, have a wonderful detailed work of what happens in this region up to the last scattering or decoupling. And then finally it escapes. But by the time it escapes, it's more or less Gaussian. And you see this sort of more or less Gaussian distribution. And that is apparently what you see. What is that? Well, it's about 10 times, it's about 8 times the diameter of the full moon. So you would have spots in the sky where the increase in the background temperature is something like about 30-fold, I think, for the strongest ones. And so you expect to see these spots in the sky. Do you see them? Well, according to the analysis that's Christoph Meissner technique he introduced, and how Daniel An looking in detail at the Planck data and then the WMAP data, and we seem to see these points in the sky. The confidence level that they're there, according to the analysis, is about 99.98% confidence, which is much stronger than I should say that the Polish school also looked at the rings that I mentioned before using a completely different analysis, and they found a 99.4% confidence level. This is a much stronger confidence level. Where are these points? Well, there's not, the analysis doesn't tell you where they are, it just tells you they're there. But Daniel had another way of looking, and he found several such points. I'm not so sure you can trust all of them. However, the 5 strongest ones in the Planck data are seen also in the WMAP data in exactly the same places. So I would trust all those. there's a sixth one in the WMAP data, which if you look back in the Planck data, you see that's there too. The sixth one, I think, is the sixth strongest one in the Planck data, in the WMAP data, which is also in the Planck data. So those 6 points I would consider to be pretty good evidence for Hawking points. So I think I'll leave that with you, and I'd be very glad to answer questions on this topic. Thank you very much.
Thank you, Roger. Let's unmute and give Roger a big hand. Roger, there have been an enormous number of questions in the chat box.
Okay.
Now, the organizers have told me that I think we don't have time enough to answer even a few of them because there's just so many. So they have decided to send you those questions after, towards the end of the day.
Well, I hope they select them because I don't think I can answer.
Yeah, I understand. I definitely, they will select, I hope.
If you could
they are
send
listening to you.
The 10 most interesting questions, say.
Okay, good. So maybe there are 2 of them here, which I think I can ask you. I mean, I can read them out. So one question is, and I don't know who has asked this question, but let me ask it anyway. What should be the measure of gravitational entropy? Can we define it in terms of geometrical quantities, even when a black hole is not present? That's the question.
I think that the trouble with this, you see, people often worry about this, and I agree. And in fact, wrong reasons have been attributed to me, saying it's something like the square of the Weyl curvature. That's not, I've never said that. It's certainly not that. I don't know a good measure. You see, the trouble with entropy when applied to stars, I mean, gravity, is you've got the individual stars, but then you've got the stars among themselves, and they start to spiral in and so on. Whereas if it was gas, then you see you're talking about molecules and you don't see them. And so you talk about averages. But when you're talking about stars, you can see the individual stars. So it's not really, maybe you could imagine them smeared out and talking about an entropy of a star distribution. I have never tried to do that. I mean, imagine the stars smeared out to a sort of gas-like quantity, and then you could maybe attribute a gravitational entropy there. I don't know of a measure of entropy. All I've done is to take the Bekenstein-Hawking formula, and it's such an extreme measure in the sense that it gives you quite reasonably, I think, a very, very large entropy because black holes are extraordinarily irreversible. And I think it makes a lot of sense. I think from many, many reasonings, you can say this is a very good measure of the entropy. And I have no quarrel with it at all. But I don't have a good overall measurement of entropy. So you might want to attribute an entropy to a star, say how much of the entropy in the star is due to its gravitational contribution. I imagine it's certainly relatively small compared with anything like what you get for a black hole, and no question about that. But I don't have an answer. I certainly would not take the square of the Weyl curve. It's got the wrong dimensions and so on. You might take a few integrals of it, you see. You could do something like taking a potential for the Weyl curvature, taking a double potential. I mean, you can do something which looks like having the right dimensions, that sort of thing. You can make a guess at that. I haven't followed that up in any detail.
Okay, I think I'll take one more question. Would conformal cyclic cosmology imply a change in the cosmological constant over time?
The way the equations are written is almost that the cosmological constant is the one thing you definitely do not change. It doesn't mean that it doesn't change. In fact, it doesn't. People do often ask me this kind of question. And certainly John Wheeler, I remember when he talked, not this kind of model, because he didn't know about this kind of model, but the older Friedman bouncing models and things like that, where he did speculate about constants of nature changing from eon to eon. I was never too keen on that. I would much prefer the constants to to be constant through the transition. And once you've got equations, you see, you have to have some equation governing the way the constants change, if they do change. You might have such a thing. I would simply only mention one thing, which tells me that if they change, it's not an absolutely drastic change. And the reasoning here is that if you look at, well, analysis mainly done by Paul Todd and some other colleagues, where they looked at the sort of time where black holes start to run into each other. And that would be something like where we are in the eon. So when you draw the conformal diagram, you see you've got Big Bang, then crossover. So one crossover and then the next crossover. We are about 3/4 of the way up this picture. And the black holes start to run into each other in a serious way at around about the same time. Now, if you think of that as the earliest time that supermassive black holes can run into each other, that gives you a limit to the size of the rings that you could get in Vahe's analysis. The limit to this is about 40 degrees across the sky. Now you can look at the rings, the biggest rings in Vahe's analysis, and you see them, and they are around about 30 degrees or a bit more. So you see something which is pretty consistent with that. That is to say that they're not radically different. You don't see them, cutting off at 10 degrees, or you don't see them at 70 degrees. You see them at a sort of scale which is consistent with the picture that the black holes in the previous eon started to run into each other when the galactic clusters started to bang into each other. You see, we're around about now, in a sense, we're going to run into the Andromeda galaxy. And I don't know how long that will take, but it's not so far off from now, in quotes. So I think it's indicating that the universe doesn't completely turn itself upside down into something very different with the numbers. But you see, if they don't evolve, you want equations telling you how they evolve, because the transition from one eon to the next, in a certain sense, is very smooth. It's not a dramatic thing in a certain. I mean, Christoph Meissner had a very good worry about whether the Planck scale is going to come in and wreck everything. But according to the calculation he did, you get away with it without having to worry about the Planck scale, and you can follow your equations quite smoothly from one eon into the next and do serious particle physics on the other side without having to worry about things which we have no idea what goes on. So I think there's good scope for trying to match features in the future with features in the past. And this was a question that Jim Peebles raised with me. Can you actually look at the remote future and see what constants are involved in the structure of the remote future? I mean, how much matter there, how much hydrogen there is, and so on and so forth, and compare that with in the Big Bang, the unknown numbers there. Do they tie up in some way? That would be very interesting to see.
Okay, thank you. I think 10 questions will be sent to you, Roger, by this evening. They will be by tonight. The organizers are requesting you to have a look.
I'll have a look.
Of course, answer at your leisure.
I think I have to put a cap on the number of questions. I hope 10
yes,
is
10.
If you find an 11th question was absolutely fascinating.
And then the 12th. Okay. All right. Thank you so much, Roger, for this brilliant talk. Very illustrative and beautiful. Let's all thank Roger for this talk. Wonderful talk.
Thank you very much.
Most welcome.
Okay.